In this second video from 10.5, we'll look at the arc length in polar coordinates, taking a polar curve and finding the arc length of it. Again, not deriving the formula, not the integral formula, but just, showing you the integral and then how to evaluate it. Of course, things are just a little bit different here because of the polar coordinates. Let's give our definition. Let f be a function whose derivative is continuous on an interval from alpha to beta, so theta is between alpha and beta. The length of the graph of r equals f of theta from alpha to beta is the integral from a to b of f of theta squared plus f prime of theta squared, all under a radical d theta. So that looks very similar to the arc length formula that we're used to, just a bit different. Now, this comes to us a little differently because of the definition of a derivative for a curve in polar coordinates, right? It's not just like f prime, right? We try to find the formula for dy dx, and that has a specific formula. So our original arc length formula looked like 1 plus dy dx squared down here. So when I manipulate that dy dx, we end up with all of this up here. So I'm omitting all of that for this video, but that's what's going on in the background. And because r is f of theta, we just replace r and r prime with f and f prime. Of course, this r prime is the derivative of r with respect to theta. Okay, not dr dx, not dr dy or anything like that, but dr d theta. And of course, we integrate from alpha to beta. Okay? And I'll just do one example here. Find the length of the arc from theta equals 0 to 2 pi for the cardioid r equals 2 times 1 minus cosine theta. Okay, we found horizontal and vertical tangents of that same cardioid, that same function there in one of the previous videos. But now I want to find the actual length. And from 0 to 2 pi, that's one entire revolution around. And for this specific function, that will really be the entire kind of closed curve, right? It's when the curve starts and then comes back to itself from 0 to 2 pi. I'll drop a picture of this function in again for that. So I write down my formula. S is the integral from alpha to beta, square root of r squared plus r prime squared, all with respect to theta. Since r is 2 times 1 minus cosine theta, my derivative should be 2 times sine theta, right? Derivative of 1 is 0, minus derivative of cosine should be a minus sine, minus a minus sine, or plus sine. So I'll plug that in and I'll square it into my formula here. Of course, integrating from 0 to 2 pi, those were given. I'm not going to make you find those. Of my function r squared, there it is, and then for r prime goes into sine theta squared. And the rest of this will really just be manipulating under that radical and trying to get to a form that we can actually integrate by hand. Okay, so I'm going to square both what's in my two shades of pink there. When I square both of those, I see the following. Well, for the first one, we probably want to write that 2 distributed in before we square. So that's the same as 2 minus 2 cosine theta. And when I square that, I should get a 4 minus 8 cosine theta plus 4 cosine squared theta. Okay, so that's foiled 2 minus 2 cosine theta. And then I have 2 sine theta to square, so really all that is 4 sine squared theta, d theta. Now I notice this right here, 4 cosine squared plus 4 sine squared. Those have a common factor of 4 that I'm going to factor out, but also because I see a sine squared plus cosine squared, and that I can boil down to be 1. When I factor out 4, I see sine squared plus cosine squared, which is indeed 4 times 1. Sorry about that. So writing that down again, I just worked with this guy here, and I've argued that that is 1 times 4, or just 4. So all that expression there, I will write just a 4. So there's my square root, 4 minus 8 cosine theta minus just a 4. I'm sorry, plus a 4 with respect to theta. Combine the 4's and I end up with an 8 minus 8 cosine theta. Okay? And in my next step here, I'm just going to factor out those 8's and see if I can manipulate anything further. So I see under my radical, I have 8 times 1 minus cosine theta. Okay, I can work with that square root of 8, right? I know I can split apart the radical, but what to do with this square root of 1 minus cosine theta? What to do with this here? Now, we know 1 minus cosine, or 2 theta over 2 is sine squared. That's like our power reduction formula. So actually, let me write that down. Sine squared of x equals 1 minus cosine of 2x over 2. And I can manipulate this a little bit to extract 1 minus cosine of theta. I just got a little bit of wiggling around to do. If I multiply both sides by 2, I see 2 sine squared. Now x here, x is really acting like theta over 2, because if I want to write down cosine of theta, if this 2x here should be cosine of theta, then x is like theta over 2. Okay? And that leaves me with 1 minus cosine of theta here. So really, that's where that comes from. Oops, sorry. Getting ahead of myself. That's where that comes from. I'm just kind of shifting around the formula that I already know, and this still applies here because of the way theta and x are related. So basically, I've just written that theta is equal to 2x, so x is theta over 2. Okay, so what I'm going to do is plug this all in for 1 minus cosine of theta, and the nice thing about this is because I'm substituting 1 minus cosine of theta with 2 sine squared theta, but it's under a radical. So the sine squared is going to cancel with the radical. Now the 8 under my radical here, I'm going to bring out as a 2 radical 2, right? Square root of 8 is the same as 2 radical 2. And then I have square root of 2 sine squared of theta over 2 d theta. Okay? So I can then take the square root of all that. Again, this square root of 2 is going to come out front just as the square root of 2, but it's multiplying what's already out there as 2 radical 2. So what I have is 2 times radical 2 times radical 2. That's 2 times 2. I should get a 4. Integral from 0 to 2 pi. And the square root of that sine squared is just sine of theta over 2. And that's pretty easy to integrate. I get a 4 negative because antiderivative of sine is minus cosine. An extra 2 because I'm integrating sine of theta over 2. Okay, we can use sub that if we want. But indeed, to cancel the 1/2 I would get from the derivative of the inside of my function here, I need to cancel that with a factor of 2. So I see 2 cosine of theta over 2 evaluated from 0 to 2 pi. Okay, so that boils down a little bit more. I see a negative 8 times. What do I get when I plug in 2 pi? Well, that's the same as cosine of pi then, when I plug in 2 pi for theta. So cosine of pi should be a minus 1. Minus what I get when I plug in 0. Cosine of 0 is a 1. So there I have minus 8 minus times a minus 1. That's minus 8 times negative 2 is 16. Okay? So the length of my curve, my cardioid, from 0 to 2 pi is actually 16 units. Now what does that look like? Here's my screen grab from Desmos, again, the same one you saw before. In fact, there's still those tangent lines on there. But really what I'm looking at is the length of the actual curve when theta is 0 all the way to when theta is 2 pi. So that's really all the way around. I colored it backwards, if that makes sense, really. I should go counterclockwise. My left-handedness made me color it the opposite direction. But really going from 0 to 2 pi, the length of that curve, length of the whole cardioid, is 16 units. Okay? All right, thanks for watching.